Hi, everybody. Ivenis Pita will be giving our 1-hour compass seminar today. Ivenis is a fifth-year PhD candidate in meteorology and physical oceanography, advised by Dr. Marlos Goes and Dr. Ben Kurtman. Ivenis earned an undergraduate degree in oceanography from the Federal University of Bahia in 2016, during which he participated in an 18-month exchange program at the University of Western Australia. It was during this program that Ivenis met his wife. Next, he earned his master's degree in meteorology at the Federal University of Rio de Janeiro, during which time he served as chief scientist of the AX97 XBT transect in the South Atlantic. This data is now being used in Ivenis's current work, as we'll see in a few minutes. And outside of Rosenstiel, Ivenis loves to walk his dog, and I'm sorry you didn't bring him here today.
Thank you for the introduction. So today my talk will be about the South Atlantic Meridional Overturning circulation and associated heat and freshwater transports from sustained in-situ observations. I'll divide my talk in 5 parts. First, I'll show a little bit of my motivation and background, where I'll focus a little bit more on the Atlantic Meridional Overturning circulation for those who are not familiar. We'll talk a little bit of the in-situ data that is available in the South Atlantic, and moving to the second part, I'll talk about how I implemented the AMOC, that's the acronym that we decided to use, and also the third part goes to expanding the estimates for the south in the South Atlantic. The fourth part is looking at large-scale patterns, and I'll finalize with some concluding remarks. So starting with the first part now, what is AMOC, or Atlantic Meridional Overturning circulation? So AMOC is the Atlantic branch of the global ocean circulation that is really important because transports heat, as we call the meridional heat transport, MHT, and freshwater, FWT, and also carbon and other properties across the ocean. It's divided in upper and lower limb. The upper limb, as we can see in red here, in the Atlantic there is 2 entrances for the upper limb. That is the cold water route and the warm water route. The cold water is from the Drake Passage and Malvinas Current, but it's also in the upper ocean. It's not the lower limb, just to be clear. And the warm water route comes from the Agulhas Passage, Agulhas leakage and rings. And in blue here we have the lower limb, or the deep water flow. So the AMOC is very likely to weaken this century. That's what some IPCC model projector says, with a certain degree of confidence, and that would influence, that would have various impacts in the weather. The AMOC is one of the tipping points of the climate change. So it could relate to drying the Amazon, disrupt East Asian monsoons, and also cause heat to build up in the Southern Ocean, which would accelerate the Antarctic ice loss. Especially in the South Atlantic, there are some researchers, some studies that show the importance of the freshwater transport, more specifically the overturning component of this freshwater transport, which is the MOV. That it's related, it's linked to the AMOC instability due to the salt advection feedback. So there are 2 scenarios, if the MOV is positive or if the MOV is negative. So when it's positive, it means that the Atlantic basin is importing fresh water, and in a possible AMOC weakening, this would lead to less freshwater convergence in the Atlantic. So more salts will build up in the Atlantic and will lead to a stronger AMOC. So this would create a negative feedback. In other means, the possible AMOC weakening would cause a stronger AMOC. That's why it's a negative feedback which stabilizes the AMOC. So it's a stable state. On the other side, if MOV is negative, it means that the basin is exporting fresh water. So in a possible AMOC weakening scenario, there would be less fresh water export in the Atlantic. So more fresh water available in the Atlantic would lead to a weaker AMOC. So that would result in a positive feedback. So initial weakening would lead to more weakening of the AMOC. Also, there are some challenges to model the AMOC, and that's about the sensitivity of it. So different model resolutions would lead to different driving forces of the AMOC. So it's really important to have more observations to calibrate and improve those models. But those observations, they are somehow limited. In the South Atlantic, we have two observing systems, the TRACOS and the SAMBA array, TRACOS in 11 south and SAMBA in 34.5. Those estimates, they have some operational challenges, and for the TRACOS array in 11 south, there are some gaps in the data, but it shows that there is an increase in salinity at different decades, that some hypothesize that could be due to Agulhas leakage influence. Further south in 34.5, a critical area for the AMOC, it shows that has a stronger variability, and the eastern boundary it's one of the main driving forces of the internal signal at 34.5 south. Also, those in-situ those observational records are too short to assess a long-term AMOC variability. And as I mentioned before, there are some observational arrays. They have some difficulty in observations with different strategies and different methodologies to estimate the AMOC. So there are also some synthetic estimates, which leads to greater, which infers the AMOC from leverages altimetry and in-situ data. Those are located in 20, 25, 30, and 35 south. Those synthetic estimates, they provide a longer time coverage for the AMOC, and they show that the ratio between the meridional heat transport and the AMOC at 35 south is 0.04 petawatts per square, and it tends to increase as moving northward. And at lower latitude, so around 20 south, there is the Ekman and the geostrophic components of the AMOC, which I'm talking more in the future. They are in phase, as you can see here, as they are in phase here, and at higher latitudes they are out of phase. But also in higher latitudes they have a stronger annual cycle. So the AMOC at the moment is being estimated from fixed observational systems, model, reanalysis, and synthetic estimates. Also there are some mapping strategies that are used to improve those observational systems, and it showed that leveraging Argo and expertise are a good way to improve the AMOC, meridional heat transport, and also the boundary dynamics. So it's really important to use those in-situ data, those sustained observational data to improve those estimates. But also the mapping method used to do that is one of the main sources of uncertainty in global products, as ocean heat content estimates and all. Here we have the Argo trajectories for the last 6 months in the South Atlantic, and here are some of the XBT high density lines in the Atlantic. So we have some it's going to be really useful for us in this study. So moving on for part 2, where I implemented my system, which I call AXMOC. I call it AXMOC because it's Argo and XBT based Meridional Overturning circulation, or AXMOC. So our goal is to obtain a cost-effective estimate of the AMOC and also the associated heat transport. For the first part, it was focused on 22.5. I'll talk a little bit more why we chose this latitude. And the objective of this chapter is to estimate the AMOC and the meridional heat transport from 2007 to 2020, and in both the geostrophic and Ekman components. Also, we want to analyze and compare the AMOC and the meridional heat transport variability on both seasonal and internal signal, and with other available time series. So our observations goes mostly for temperature and salinity profiles from Argo and XPTs. We selected this latitude 22.5 because we would maximize the Argo, the XPT transect that which is the AX97. We might maximize the data coverage there. So in total, we use approximately 40,000 profiles from 2004 to 2020, and I select them in a box between 15 south and 30 south. And Argo measures temperature and salinity. XBT measures only temperature. So we have to infer the salinity from the temperature profile given from XBTs. But also they don't provide the entire water column, the data for the entire water column. So we have to do a padding to complete this profile all the way to the bottom, which we use the World Ocean Atlas climatology. And we masked our bathymetry with a topo 5 minutes. And then we have to mapping our data for a specific transect. In this case, it's the 22.5. So we use the weighted average method. So give a higher weight for those profiles that is closer to my reference transect and the reference time. We have two parameters that we set: a temporal window and radius of surge. So in total, we have 20 subsets ranging, because the temporal window ranges from 30 to 180 days, and the radius of surge from a quarter degree to 5 degrees. And with those 20 subsets, we want to maximize and to optimize our section, which we do it by using the cost function, which is the root mean square error. So if we minimize these cost functions by comparing the dynamic height and the altimetry data, the absolute dynamic topography. The altimetry data is monthly resolution, a quarter degree, and we detrended and interpolated to the AXMOC transect. Then we will have the optimized temperature and salinity sections. That it's also monthly and a quarter degree resolution with 140 predefined sea levels. Here we can see the parameters that the distribution of those parameters that we use, the delta R and delta T, they are pretty noisy given the data distribution, because it's uneven and random. And the median parameter select for delta R varies between half degree and 1 degree, and for the temporal windows from 60 to 90 days. And the root mean square error between the altimetry and the In-Situ data, it's lower than 1 centimeter. But here we can see on the right that how the tuning my data with the altimetry is able to provide a good picture of the dynamical of the sea level across the section. Then we have the optimized temperature and salinity sections. We would now estimate the AMOC and, in this case, the meridional heat transport. So we have both geostrophic and Ekman components for the AMOC and meridional heat transport. The geostrophic is the density-driven component, and the Ekman is the wind-driven. For the Ekman, we use the surface wind stress to estimate the Ekman velocity. We use ERA 5 reanalysis data for that. And for the geostrophic component, we use the optimal temperature and salinity sections that we obtained. and we use the reference level for the geostrophic component at 3,700 meters. We decided to use this level because it delimitates the deep and bottom waters at this latitude. To ensure the mass balance, we use a velocity correction to make sure that there is it's conserving mass or section. And the AMOC strength is calculated by the maximum strength function of the AMOC. It's normally around 1,100 meters. Then we compare our data with some synthetic profiles, 20 and 25 south, which is also monthly at 40-degree resolution, and we use data between 2005 and 2020. And we also use some Cliver goal-shaped transects. We have the A9.5. We have two repetitions. Those are CTG stations at 24 south. And we have two repetitions, one in 2009 and another one in 2018. So now moving out to the results, we can see how our surface field was improved. We can see the westward propagating signals. Here in the middle, it's our data. And it was improved against the Argo gridded product, the RG Argo. It shows, we can see those westward propagated signals that goes all the way from the eastern boundary to the western boundary. So it highlights the importance of the eastern boundary for the basin, as a forcing for the basin. And also we are able to resolve some intense events, like those specified here, and also in the western boundary here. Because it also highlights the importance of high density XPT data, because it matches this western boundary. That we have a lot of XPT data there it's not in a high density mode, so on average every 2 to 3 months you have one transect there, and also a little bit west of 10th east, for example, we have another some intense events that we're able to resolve with our method. Moving on for water mass distributions, we are able to see some water masses by the mean velocity section. We have two cores of the North Atlantic deep water, one on the eastern boundary and another one on the eastern and another one on the western boundary. So it means that the North Atlantic water bifurcates north of 22 south, and we can also see those signals, the water mass signals from the local maximum of salinity and dissolved oxygen. The dissolved oxygen, we use the A95 data, so the goal-shaped data. And there is a slight difference between the eastern and the western boundaries. The western boundaries tends to be higher, and the local maximum tends to be a little bit more pronunciated, like with higher values of salinity and also of dissolved oxygen. We also can highlight that the Antarctic bottom water, the northward flow here, it's confined by topographic features on the of the Trinidad Island Mount Ridge. When we compare to A95 data, here we show a little bit of the volume transport in isopycnal layers. We have two plots, one on the left for 2009 and for April 2009, and another one for March 2018. Sorry. So we have a good agreement between our data that it's in black, the black dot, and the A95 data, which is those blue triangles here. And also we have the black line is the inverse model that shows the goal-shaped and Cliver data as well. So we have a pretty good agreement, especially in the upper ocean. That's where we have the temperature and salinity data from XPT and Argo. Moving on for the AMOC time series, we see that the AMOC mean value is 16.3. It's a positive flow. The geostrophic is more intense, 21, but it's counterbalanced by the Ekman component, which is negative. So they have opposing directions. In terms of what drives the AMOC, in this case, it's density driven by the geostrophic component, as we can see here, both in the interannual raw and interannual signals. The AMOC is highly correlated to the meridional heat transport. That's also a given from other studies as well. So we have a correlation higher than 0.95, and we found, as you saw here from synthetic estimates, we also see the components, they are in phase in the seasonal signal, and we found no significant long-term trend. In terms of the influence of the boundaries, we divided the AMOC geostrophic in eastern, interior, and western boundaries. We found a higher correlation between the western boundary and the AMOC, so it suggests that the western boundary anomaly drives the AMOC variability, and followed by the eastern boundary. And there is also an interesting compensation between the interior and the eastern boundary with negative correlation of 0.5. In this case would be the blue lines and the red lines, so they are opposing. So some takeaways of the second part is that we obtained the first long-term in-situ AMOC estimate at 22.5. One positive is that Argo and XVT coverage we have a good coverage to estimate the AMOC and the meridional heat transport. Especially, it's really important to highlight the XVT coverage at the western boundary current. That was really important for us to get this western boundary influence on the AMOC. We also found the North Atlantic deep water is bifurcated north of 22.5 south, and also the importance of the western boundary on AMOC anomalies. But there's also room for improvement, and how could we, in this case, how could we further validate our method? So we came up to the idea to compare to alternative methods and also to direct estimates. So one good way for us to do that is at 34.5 south, where we have the SAMBA observing system, the AMOC observing system there, which leads us to the part 3, which is expanding the AMOC further south. So in this case, our goal is to expand the AMOC coverage to 34.5 south, and as the freshwater is one of the it's really important in the south. At this latitude, we also want to estimate the AMOC, meridional heat transport, and the freshwater transport. And we decide to do that by comparing also the optimization method that we previously established and a machine learning approach. So the objective was to estimate those time series from 2005 to 2023, so bring it to update the time series, and also the geostrophic and both geostrophic and Ekman components. We're then comparing those different mapping methods and analyzing against direct AMOC estimates, in this case the SAMBA array. We then further decompose the meridional heat transport and the freshwater transport in overturning and gyre components, which I'm going to talk a little bit later about it. So the data that we use, it was around 50,000 profiles from 2005 to 2023. In this, now we selected about between 27.5 and 40 south. We also used the World Ocean Atlas to padding the data all the way to the bottom of the ocean and infer salinity from temperature profiles from XVT. But in this case, we use altimetry, sea level anomaly, and also the sea surface temperature, a reanalysis or ISST, in both daily and monthly formats with a quarter-degree resolution. For the optimal mapping, we use only the altimetry, but for the machine learning, we use both surface fields. Also at 34.5, we use the mean velocity product to be a reference level, because there is an important barotropic component there. We use half-degree velocity product that blends Argo and altimetry data. For the machine learning approach, we use two neural networks, one to estimate the temperature and another one to estimate the salinity. So we use feed-forward neural networks, or NNs. We set up them with two layers, one with 20 nodes and another one with 10 nodes. And we use 8 inputs. Most of those inputs, it's related to the data coverage. So latitude, longitude, year, transform of the day of the year, and also the depth of the profiles that we have scattered in the South Atlantic. But we also use the sea level anomaly and sea surface temperature from altimetry and reanalysis. So it would give some real world signal. And the output would be temperature and salinity. So we train those, we use 80% of those 50,000 profiles to train them. In the training phase, we use the Levenberg-Marquardt algorithm, which is a non-linear least square problems. It was a pretty standard approach that we use for this machine learning method, and it was validated on a study that used a similar approach to estimate the dissolved oxygen from Argo profiles too. In this case, the Argo BGC and the Argo core. So the next phase will be the validation phase. We have a correlation of more than 0.99 for both training and validation steps. And we have the target, which was the temperature and the salinity from those 20% of the profiles. And our predicted is the output of the machine learning of our approach. They have similar mean and standard deviations, and the root mean square error, it's 0.6 for the temperature and 0.12 for the salinity. Here on the bottom we have two TS diagrams, one using all the 20% of the data that's distributed in the entire box that we use, so 27.5 all the way to 40 south. But our aim is to estimate the AMOC only in 34.5 south. So when we select a range of all the profiles that we use for validation, that is within half degree of a reference transect, which means between 34 and 35 south, we have a much better fit, at least visually, in terms of the statistical. It was similar because we have a lot of data, so it doesn't change much on the error. For the AMOC and meridian heat transport and freshwater transport calculations, the AMOC and the meridian heat transfer were similar to what we did on part 2, both geostrophic and Ekman components. And the one difference was that we forced a barotropic component at the reference level at 1,000 meters. We used the Argo-based velocity product because we did some sensitivity analysis and shows the best mean AMOC values, as well as the bottom temperature, bottom velocity. And then we divide the meridian heat transport in overturning and gyre components. The overturning is it takes in account the zonal mean of the section, and the gyre is the residual of those values. So it highlights the structure within the section. The same for the freshwater, and we call it in MOV and MAZ. Then we compared our data with the SAMBA array, the SAMBA is daily, but we sampled for monthly values because we are dealing with monthly data as well. And the SAMBA, there is a period between 2009 and 2020, and between 2013 and 2017. So there are some gaps and needed an update in here. So there's room for improvement for us. And also we compare against synthetic profiles at 34.5, which is monthly aquatic grids, similar to those synthetic profiles in 2025 that we show in part 1. first, we want to compare the optimal mapping with the neural network. Both yield similar results. Here we show the AMOC, the AMOC, the meridian heat transport, and the freshwater transport, just the total, the sum of the geostrophic and Ekman components. So they yield similar results with correlation 0.7 for the AMOC and increasing for meridian heat transport and the freshwater transport, increasing all the way to 0.92. Also, the standard deviation of those estimates are pretty similar between all of the three estimates that we use, which highlights the robustness of both methods given the data distribution that we have. And from now on, we use the optimal method for the AXMOC, which is the same one that we use in the part 2. Comparing now with other estimates, our AXMOC estimate with another estimate, we also have the AMOC, meridian heat transport, and the freshwater. We divide them in. We have now the D35S, which is the synthetic estimate from Dong et al. 2015 and 2021, and we also have the SAMBA time series here, that we have this period between 2009 and 2010, and also this segment here between 2013 and 2017. Here we show the mean AMOC estimates for the SAMBA period, so for those two periods here only. They all have similar mean values, but the variability of the SAMBA it's known to be bigger than other estimates for the AMOC. But surprisingly, our AXMOC estimate also have it was the second highest variability, using the standard deviation as a proxy. It's the second highest variability, so it represents an increasing variability compared to the synthetic estimates. We have similar correlation between SAMBA and our data, and SAMBA and our data, and the synthetic estimates. And it's also important to highlight a weakening phase that it's observed here by SAMBA, that we can also see on AXMOC data and also on the synthetic estimate, but in a less intense way. So now, providing the entire time series of the AXMOC in both the Ekman and geostrophic components, we can see that the AMOC and the meridian for the AMOC and meridian heat transport, both the Ekman and geostrophic components have the same direction, which is it's proved to be it's known because of the wind-driven component, because of the trade winds at this latitude. Sorry, the west axis in this latitude. And the geostrophic component drives the internal signal, as we can see here. There's a great the solid line, the thicker line is the internal signal, and we can see from the correlation between the geostrophic component and the total time series, for the AMOC, for the meridian heat transport, and it's a little bit lower for the freshwater, but we can talk more about it. And we can the weakening that we saw on the SAMBA, on the first period of the SAMBA in 2009-2010, it's our data suggests that this weakening is driven by the geostrophic component. So we see this weakening because the geostrophic drives the internal the total AMOC in the internal signal. But when we talk about the seasonal cycle, here on the right, we can see that the Ekman component, which is in red, it drives both the AMOC meridional heat transport and also the freshwater transport. And the geostrophic component is out of phase, similar to what the synthetic observations, synthetic estimates have told us. But for the freshwater component, we can see that there's a weaker geostrophic signal. It's pretty much around zero. There's a really weak signal, really weak variability the seasonal. For the total period that we used between 2005 and 2023, the AMOC had a mean value of 16.8. The mapping uncertainty that we estimated was from the 20 byproducts that we had. So we calculated the standard deviation for each point in time, and then averaged the standard error for those 20 ensembles, which we assume to be the mapping error. And we have 0. And the variability of the AMOC is even higher than the one that we selected for that we estimated for the SAMBA period. So if the variability of SAMBA, if it was entire time series, would probably be higher as well, higher than 5.2, if I'm not wrong. And the freshwater component, it's slightly negative, but we can talk more about it later. So now we can decompose the overturning and the meridional heat transport and the freshwater as well in overturning and gyre components. We can see that the overturning and gyre, they have opposite directions. Here on the plot we have the overturning also further decomposed in geostrophic and Ekman components. As the orange is the geostrophic overturning component, red is the Ekman overturning component, and the blue is the gyre component for the meridional heat transport. On the internal signal, we have the overturning component drives the meridional heat transport, and the gyre has no correlation with the meridional heat transport. But the overturning, it's driven. The overturning component, both components of the overturning, the geostrophic and the Ekman component, also has a good correlation with the meridional heat transport. For the seasonal signal, it's only the Ekman component, the wind drift overturning component, that influences the seasonal cycle for the meridional heat transport. We also have the geostrophic components out of phase, similar to Ekman and geostrophic, so it was expected, and a small contribution for the gyre. Now for the freshwater component, we can also decompose those in overturning and Ekman components. There are some freshwater estimates from observational studies, but they are not a complete time series of it. It's points in time. So normally a few points, like one every decade, or with the XBTs, there are some. This data could also be used for freshwater transport estimates as well. So it's a higher frequency in this case. Some climate models show that there is an overturning component bias. So it's really important to estimate the overturning here. So climate models tend to set a MOV as positive in this latitude, which would indicate a stable AMOC, but as you can see here, our MOV is negative, so it would indicate an unstable AMOC. There are some studies also that show a decoupling between the AMOC and the freshwater. What is that? It shows that the freshwater content is not driven by the AMOC, so there's not a good correlation between the AMOC and the overturning component of the freshwater content, and we can talk a little bit more about it. Our results partially agree with this, but we took a further step to analyze this and shows that at the interannual signal, it's the MAZ, the gyre component, drives the freshwater with a correlation of 0.5, and the overturning, the correlation is 0.36. But when we further decompose the overturning component in geostrophic and Ekman, it shows that what really drives the Ekman, this was really interesting for me, that what really drives the AMOC what really drives the freshwater is the wind-driven overturning component, which are a correlation of 0.64. while the geostrophic, the density driven, has no correlation with the freshwater transport. And in the seasonal cycle, we see that the Ekman component also dominates, as in all other estimates for AMOC and meridional heat transport. And there is a balance between the azonal and the geostrophic. Azonal is the MAZ, and the geostrophic component of the overturning. We can also analyze the meridional heat transport in the freshwater in Z layers at depth, and we can see that the overturning component for the meridional heat transport, in this case, it drives the meridional heat transport in all the depths, because the gyre is only limited to the first 500 meters, the gyre component. And we can also infer that around 70% of the all meridional heat transport is confined in the upper 1,000 meters. For the freshwater here, we can see that there is a balance between the overturning component, which is in red, and the azonal component, which they are balanced in the upper 500 meters, which results in almost zero freshwater transport in those 500 meters, except from the upper part, which involves the Ekman component, so the overturning Ekman, which brings the freshwater to a negative value. And also in areas deeper than 500, we can see that the MOV influences the overturning component influences the freshwater. But interesting also, between 500 and 1,000, the MOV, it's negative. It also further decreased the freshwater, the gain that was driven by the Ekman component at surface. Also, here we show a little bit of some climate model salinity bias. This is a model that shows a decrease in salinity, especially the upper eastern and interior and eastern boundaries. And this would result in this is the MOV for this. This is the same plot for the MOV for the climate model. So it shows a weakening of the MOV in this case, right? Because there is a positive MOV, which is also why they have this bias why climate models tend to have a positive MOV because of the salinity bias here, and we can see that in this plot that shows the positive here. So the takeaways of this chapter, this part, is that both optimal mapping and neural network methods obtain a similar result. So that's a really plus for the mapping strategy used. There is a good agreement. AMOC has a good agreement to previous estimates and a similar variability to SAMBA, and we can now provide the longest continuous in-situ based AMOC time series at 34.5 that can be merged with direct observations to improve the estimate of AMOC. In this case, it's really useful to make or even merge the AMOC, the AXMOC and SAMBA time series, or use both data to leverage the estimates in 34.5. Also, the AMOC exports freshwater in 34.5, so they have a negative overturning component of the freshwater. And the wind-driven overturning circulation dominates the freshwater transport, followed by the gyre component, the azonal. The overturning component drives the meridional heat transport with a greater geostrophic influence on interannual signal and a greater Ekman influence on seasonal cycle. And in the upper 1,000 meters, we have around 7% of the meridional heat transport. Moving on for the fourth part, we're looking at large-scale patterns. So here we have the upper 300 meters temperature and salinity average for AXMOC, our data, for ORAS-5, a reanalysis with a quarter-degree resolution, and EN4, a database with a temperature and salinity database with 1 degree resolution. So the ORAS-5 reanalysis can represent some patterns that we can see on AXMOC. And more specifically, there is this high-low-high pattern in both temperature and salinity between 2008 and 2017. That it's present on ORAS-5, AXMOC, and also in a little less extent in EN4, but it's also visible there, which suggests there is a gyre scale pattern in the South Atlantic. This is kind resembles the meridional heat transport and the freshwater anomalies that we found. But when we analyze our data and take zonal average temperature and salinity, the pattern of the zonal average temperature and salinity, here is the temperature anomaly and here is the salinity. In the upper 1,000 meters, we can also see this high, low, and high patterns. So in both temperature and the salinity anomalies. So, but in this case, when we average them in the entire section. So we wanted to analyze more what would be this link between 34 South and the South Atlantic pattern. So we did a single value decomposition. It was applied to retrieve the joint modes of the temperature and salinity in the upper 300 meters. And the mode with the strong correlation was the second mode, and then we analyzed it here. We did the same for the EN4 and ORAS-5. For the ORAS-5 that has that better agree with the AXMOC time series. We obtained a 22% of explained variance, and there is a high variance in both temperature and salinity along the western boundary and around the subtropical gyre. So it shows that there is something happening, and we can see here on the principal component, the principal component that has a similar pattern with the up and down, the high, low, high value that we observed in temperature, in salinity and temperature. So it's a little bit preliminary, but we want to understand more what's happening here. So moving on for the concluding remarks. At first, I'd like to highlight the importance of argon XBT for the AMOC meridional heat transport and freshwater transport estimates. At 22.5, we observed that the North Atlantic deep water bifurcates north of 22.5 with our data, as we could see both cores of North Atlantic deep water in both boundaries. Our results also suggest the importance of the western boundary dynamics on AMOC anomalies. And at 34.5, there is a good agreement and a closer variability to the SAMBA array that we could use to extend time series and few observational gaps. We could merge both products there. The AMOC exports freshwater as other observations that we have in the South Atlantic at this latitude, and which would lead to an unstable AMOC. And the overturning component, drives the meridional heat transport with 7% of its total value confined in the upper 1,000 meters. And the wind-driven overturning component drives the freshwater transport. And there is, moving on for the last part, there is a possible gyre scale pattern in the South Atlantic. There is an influence on the western boundary. There is a likely area of influence in the western boundary area. And it shows also a high, low, and high, these positive, negative, and positive anomalies in the upper 300 meters for both temperature and salinity. So with that, I conclude. Thank you.
Question?
Alex, a quick question.
Very nice presentation, Ivenis. My question is, the result that you found about the freshwater transport being really strongly controlled by Ekman, was that something that you found both with your objective interpolation analysis and your machine learning, or was that a result that was based on one or the other?
Yeah, that's a good question. We decided we haven't analyzed the neural network. We compared those two models in the freshwater, and then we decide to use just the optimal mapping to compare with other estimates. But that's a really good idea to look to see how the neural network see that as well. Yeah, we haven't looked, but yeah, I assume it would be similar because we plotted the geostrophic and Ekman components, and we see similar results for both the optimal mapping and the neural network. The Ekman component would, I assume it would be similar the results because the freshwater component, the correlation between the optimal mapping and the neural network is even higher. It's 0.92, and the Ekman component it's the same because it's era 5 data. So I assume that will be a similar result as well.
Yeah, I was just curious because the vertical profile was so sharply skewed by the surface, and you explained that your neural network was trained on surface data, so I was just wondering if it was related to that.
Yes.
But it sounds like you built that calculation not on the neural network.
Yeah. But the thing is, it wasn't on the neural network. But the plot that I showed, it's only I divided the layers, the vertical layers, in 100 meters. So it's not a cumulative plot. It's just like the transport within 100 meters. So I think that's why there was a big difference.
I have a question.
Yes.
That was a lot of good work. Well done.
Thank you.
So I was going to ask about the freshwater transport too, right? It's kind of typically, well, when I've looked into it, it's the harder one to understand.
Mm-hmm.
You know, it can be. So I wondered, you mentioned that you were surprised that I think that the freshwater transport was dominated by Ekman, if I got that correct. Although in your conclusive slide you said it's dominated by the wind-driven overturning. So
Yes.
what do you mean by wind-driven overturning? You mean the Ekman?
Yeah, because the Ekman component is only on the overturning. The influence of those is for our estimates was only on the overturning.
So it's the Ekman component of the overturning that dominated the freshwater transport, and not the gyre.
Yes,
correct?
I was surprised by that because I thought that the geostrophic component would also play the overturning density-driven, the overturning geostrophic component will also play an influence on that, but we found no correlation between those.
So why? Can you talk more in terms of your understanding of what the oceanic processes are in the South Atlantic subtropics? Why was your expectation different in terms of water masses, fluxes? Can you explain that?
Well, there are some results that show this decoupling between overturning and between the AMOC and the freshwater. I have to look back to those to check what would cause the. I think it was related to the upper 300 meters. So in this case, it showed that it was more the freshwater was driven by the salinity content instead of the circulation. That's what I remembered from the paper from Miag and Leo. Those two papers I remember reading that. So yeah, I have to look back at the paper and get back to you about it.
For example, do you think it's related to some seasonal northward transport of subtropical mode water? For example, that we might expect to be salty. I'm just wondering if you had any insight into that.
Yeah, could be also for agulha leakage, right? The influence on the eastern boundary in that. So yeah, I think would be but that's possibly like some signals that keep that are propagating northward in the Atlantic that could influence that, not related to the returning in a way. So yeah, I don't have many insights about it, I'd say. So I have to look more about it.
Any online? Nope. All right. Well, the next compass is Friday at 11 a.m. Thank you, Ivenis.